Let's look at an example, and then we'll derive our formula for parametric differentiation, and then we'll come back to the rules. But just to show you what a parametric equation might look like, you have our first example. You have x as a function of t, so in our case it's cos t, and then you have y as a function of t, and in our case it's sine of t. It's important when we're dealing with causes and sines to have a limit, so it's telling us that t, the range of t, is between 2 pi and 0, so it's the full circle for sine and cos. So let's have a look and write them down. We have x equals to cos of t, and y equals to sine t. And t is defined between 2 pi and 0. So we're looking at t in radians. Now, these are obviously parametric equations. You have x, which is defined in terms of t, and then you have y, which is defined in terms of t. Now, remember, if someone asks you to find the gradient or asks you to find the steepness, or m, we are always looking at dy by dx. Now, at the moment, looking at these two equations here, it seems quite impossible to derive this little expression of dy by dx. But as we go through it, you'll see that it's fairly straightforward. We have an x and we have a y, and we are looking for dy by dx. So the first thing that we could do is we could just differentiate them separately. So we could do dx, we could differentiate dx with respect to t, because that will work because we have cos of t that we're differentiating. So we need to differentiate it with respect to t. And then also we can do the same here. We can do dy by dt and then find our answer there. So these are two important steps. We are taking our x, we're differentiating x with respect to t, and we're taking our y and we're differentiating y with respect to t. Let's actually look at our functions and differentiate it. Cos of t, or cos of x, remember, goes to minus sine of x. In our case, it goes to minus sine t, or sine of t. And then sine of t differentiates to cos of t. These are our rules. Look back at them, but remember, with practice, we should be able to learn what these general functions differentiate to. Okay, let's ignore these numerical functions for now and look at this. We have dx by dt and we have dy by dt. We still don't have dy by dx, but think if there's any way that we can combine these two to get dy by dx. So you want dy at the top and you want dx at the bottom. Here's something you could do. You could flip this, so rather than writing dx by dt, you can write this as dt by dx. Obviously, we're going to change the other side as well, so that becomes 1 over minus sine t. So we flipped the entire fraction. So rather than dx by dt, we've written it as dt by dx. And watch what happens if I multiply the two. If I do dy by dt, and I multiply this with dt by dx, by simple algebra, you can see that the dt's here can cancel out, and then that leaves you with dy by dx. And so we've almost defined how to differentiate parametric equations. The formula for differentiating parametric equations is simply this. dy by dt multiplied by dt by dx equals to dy by dx. Some textbooks also like to define this as dy by dx equals to dy by dt, and that's divided by dx by dt. So in this case, you don't really have to flip the fraction. Just write them the same way. So in that case, you don't, like I said before, you don't have to flip the fraction. You can just divide it, because if you look at this closely, we are saying dy by dt divided by dx by dt, which when you change to a multiplication sign, you get dy by dt multiplied by dt by dx, which is exactly the same thing as we've said here. So it's really up to you, whatever you find easier. If you prefer to flip dx by dt first to dt by dx and then times it, that's fine. If you prefer to just divide it and not flip, so simply just take your dx by dt here, or this term there, and you just divide dy by dt by this term here. So either way is fine. You'll get exactly the same answer. So now that we've defined what dy by dx is, we can now come back to our numbers or our question. We are saying that dy by dx is dy by dt, which in our case is this, cos t. So we don't change that. That's not cot, it's cos of t. And then we are multiplying it with dt by dx, or dividing it with dx by dt. I've done dt by dx here, so I'm multiplying it with 1 over minus sine t. This gives you cos of t over sine of t, and remember that this is negative. We're done with the differentiation. The only things we can do now is tidy this up. So if you remember one of your identities for tan, so tan of, let's just use t, equals to sine t over cos t. So if you had 1 over tan of t, that is cos of t over sine of t. So you can see here that this is just minus 1 over tan of t. And if you really try and remember hard, you will remember that 1 over tan is the same as cot of t. Got too many t's going on. So what we've done here is actually found what dy by dx is. So the gradient of dy by dx is minus cot t, just by using parametric differentiation. Now, interestingly enough, just a little extra point here, we can also combine these two equations together just to see what this actually is. So just to show you, when you have x equals to cos of t and y equals to sine of t, if you square both the equations, so let's just square this, so then we square this, and if we square this, we square this, so we've just squared everything. Now if you try to add them, if we have x squared plus y squared, this is the same as cos squared t plus sine squared t. And look at your identities, and hopefully you'll remember that cos squared x plus sine squared x is the same as 1. So now if I just write this part of the equation and this part of the equation, you will get x squared plus y squared equals to 1. And hopefully you recognize what this is. This is the equation of a circle. So this is the equation of a circle with unit radius. So we have a circle with a radius of 1. And it's defined by parameters. So we've got the parameters t. And also we have found that the gradient of this circle is minus cot t. So it's really quite interesting with very little information and everything that you know, the kind of things that you could do. You can define what kind of function it is, you can imagine it, you can sketch it, you can find its gradient, you can find the gradients at different points. We can extend this if someone asked us to find the equation of a tangent or a normal, we can do that. And so, with very little information given to us, you can find a lot about these functions.